Okay, ladies and gentlemen, today in the lecture we're going to go do more open system second law examples. And just to give you an update on, will be Thursday, we're going to do more closed system second law examples. So I've kind of changed things around a little bit because I want to get open system and closed system kind of close together. And what I've done in previous semesters is did two classes of open system, or two classes of closed system and two classes of open system. And what happens is students tend to forget the closed system situation. So I want to make sure that we have that down and understand what's going on there. And then there'll be some practice problems, and I think it's important to do those practice problems so we understand what's happening here. So please do your best to get these things understood, and if you don't, talk to me so that we can work on them. Okay, that's very, very important here. We have an exam next Monday. Next Monday night is our third exam, so it comes just hot and heavy. Just doesn't. There's no stop in thermo during the summer. Just boom, 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 boom. Okay, so here's the problem statement that we have today for more open system second law examples. I have a counterflow heat exchanger. So I'm going to draw that counterflow heat exchanger. Big box here, and it's supposed to be closed. Here's my box. This was not the problem I was having with the computer. This is total operator error. And on the top of this, we're going to have water, or H2O, and the bottom we're going to have air. Okay, so counterflow, so we're going to have something coming in here at 1 and something leaving here at 2. And I'm going to have something coming in here at 3 and leaving here at 4. Okay? And it says saturated water vapor at, and so let's do here, state 1. It's saturated vapor. And it tells us it's 100 kPa. That's going to be our pressure. Okay, let's scoot over a little bit so I make sure I'm in your screen. Okay. Enters a counterflow heat exchanger operating at steady state and exits at 20 degrees Celsius with a negligible change in pressure. So state 2 is going to be temperature 2 is going to be equal to 20 degrees Celsius, and my pressure 2 is going to be 100 kilopascals. Now in real life, you're going to have some pressure drop that's going to occur because of a heat exchanger, but we're going to consider this to be negligible in this situation. Then it says ambient air. Ambient means the air from all around our surroundings. This is state 3. Ambient air enters at 275 Kelvin. So temperature 3 is equal to 275 Kelvin. 1 atmosphere. Pressure 3 is equal to 1 atmosphere. The air mass flow rate is 170 times that of water. So the mass flow rate of air is equal to 170 times the mass flow rate of the water. Okay. The air can be modeled as an ideal gas with C sub P is equal to 1.005. So they say C sub P is equal to 1.005 kilojoules per kilogram Kelvin. So they're telling us there, air is an ideal gas, and we can make that assumption already. But they are telling us a C sub P value, so that's telling us, hey, you get to use constant specific heats in solving this problem. Kinetic and potential energy can be ignored. Okay. They told us also here, I skipped a line, state 4. See here. Ambient air at 1 hour, and it exits in 290 Kelvin. So temperature 4 is equal to 290 Kelvin. Okay. They say for a control volume that encloses the heat exchanger, evaluate the rate of heat transfer in kilojoules per kilogram of water flowing. So I want to find out what is if we have a control volume that is this yellow line. They want to find out what is the heat transfer leaving. There's some heat transfer leaving this Q dot. So we want Q dot in kilojoules per kilogram of water flowing. Okay, so that's an interesting way to put this. Kilojoules per kilogram of water flowing. That's what we want to find. Okay, so the first thing I do, I understand now that I have, first law and second law that I can apply to this problem. So let's just look at my first law and see where it takes me. I shouldn't automatically think I should go to the second law. Q dot is in my first law. It's also my second law. But I have to think to myself, the second law doesn't really have anything that can help me with if it's reversible or not. There's two unknowns in the second law. There's going to be q dot and sigma dot that I'm going to have as an unknown. So I'm just going to go with my first law. dE dt is equal to q dot minus w dot plus the summation of my mass flow rates n times my enthalpy n plus my kinetic energy n plus my potential energy n minus the summation of my mass flow rates xting times my enthalpy xting plus my kinetic energy xting plus my potential energy xting. Okay, and I know this is a heat exchanger turning steady state. This goes away. There's no power. There's no kinetic or potential energy effects. And we're going to get ourselves down to 0 is equal to q dot plus m dot 1 h1 plus m dot 3 h3. That was what's coming into my control volume. What's leaving is going to be m dot 2 h2 minus m dot 4 h4. And we can do some substitution here because we know that 0 is equal to q dot. We know the first is going to be m dot water. It's going to be h1 minus h2 because we know that h1 and h2 are both waters. No, water's not leaving, so the mass flow rate of water at 1 and 2 is going to be the same. And then we also know that mass flow rate of 3 is mass flow rate of air. That can be h3 minus h4. Okay. I'm trying to solve for q dot, so I move this over here and say q dot is equal to mass flow rate of my water times mass flow rate of my air times h4 minus h3. All right. Now we start getting it. We've got it down to where we need to. Now we go to the problem statement and find out what information do we have from the problem statement that we can put in here. Well, we know that this is going to be mass flow rate of water. We can't do anything really with the water, h2 minus h1. But we can say the mass flow rate of the air, they said, was what? 170 times the mass flow rate of my water. And then we can replace our delta H with C sub P times T4 minus T3 because we're doing constant specific heats. Okay. Now I have mass flow rate of water on both of my equations. So if I can both of my terms, and so I can divide by mass flow rate of water, and now I get q dot over the mass flow rate of water is going to be equal to h2 minus h1 plus 170 times C sub p times T4 minus T3. Okay, so this is going to give us what we wanted. We wanted heat transfer, which is going to be in kilowatts, or heat transfer rate in kilowatts. And mass flow rate of my water is going to be in kilograms of water per second. Well, what's a kilowatt? A kilowatt is a kilojoule per second, and then we're end up units here of kilojoules per kilogram of water. That's what we're going to have there. So that's our unit work out fine. We can check that all we want. Okay. So if I go through here and I look this up, and I'm not going to pull up my tables. I encourage you to pause and to see if you can find the table values for this. But by now I think we should be pretty comfortable with finding table values here. H2 is going to be 83.96. H1 is going to be 2675.5. This is going to be kilojoules per kilogram. Plus 170 times C sub P, which is equal to 1.005 kilojoules per kilogram Kelvin. Now remember, this is actually kilograms of air, but we had a term here. This mass flow rate of air was there, and we replaced it with 170 times mass flow rate of water. So that kind of converts the units. So this is all going to be kilograms of water. And then T4 minus T3 is going to be 290 minus 275. Okay, and when we put all this in here, we find that we're going to have negative 28.76 kilojoules per kilogram. Okay, so we're having heat leave this, negative 28.76. That makes sense. Heat should be leaving this control volume, and negative 28.76 is a good reasonable number here, kilojoules per kilogram. Okay, so that's part A. Nothing changed. That's an old first law problem that we could have given you in chapter in the second exam. Okay, but now it says enlarge the control volume. So now it says no, don't make it just what it is. Enlarge the control volume that includes the heat exchanger and enough of its immediate surroundings that the heat transfer occurs at the ambient temperature. So now I don't want to look just here. I want to make my control volume a bigger control volume. Now this is my bigger control volume, and I'm going to say that this boundary here, this boundary is going to be at 275. Now we're saying that we've got a big enough boundary that now the heat transfer that crosses past there is going to be at the ambient temperature. They want to be determined what the entropy production is. Okay, so now that comes into now we would have to use the second law here. So we're going to use ds Cv dt is equal to the summation of the heat transfer rate and the temperature at which that heat transfer rate occurs, plus the summation of my mass flow rates in, entropy in, minus the summation of my mass flow rates exiting, entropy exiting, plus sigma dot. Okay, we're still at steady state, so this goes away. Okay, and we have one heat transfer, so we don't have to worry about the summation here. And we found this on the previous problem, and we know the temperature boundary because now that's given to us as 275. So we go through here and we say, okay, here's what we're going to get. 0 is equal to Q dot all over temperature of the boundary plus m dot 1 S1 plus m dot 3 S3 minus m dot 2 S2 minus m dot 4 S4 plus sigma dot. Okay, we're going to join these things together again. Q dot over temperature of the boundary plus mass flow rate of the water times S1 minus S2 plus the mass flow rate of the air times S3 minus S4 plus sigma dot. Okay, I move sigma dot to the other side of the equation. I'm going to get sigma dot is equal to mass flow rate of my water times S2 minus S1 plus mass flow rate of my air times S4 minus S3 minus Q dot all over temperature of the boundary. Okay, well, I'm going to have to look up some things here to make sure that I get this right, and I'm going to have to use my all the stuff here. I also want to find my units here. I want to find this in kilojoules per Kelvin per kilogram of water. Okay, so I have to again do my conversions here. I have sigma dot is equal to mass flow rate of my water times S2 minus S1 plus this is going to be 170 times the mass flow rate of my water, and now I have to use the constant specific heat way to do it, entropy, that we talked about when we developed our TDS equations. So this is going to be C sub P times natural log of T4 all over T3 minus R natural log of P4 all over P3. Okay, so we divide this all by mass rate of the water. And we also know here that our pressure, we can assume a negligible pressure drop in our heat exchanger, and so this can go away as well. And we're down to S2 minus S1 plus 170 times C sub P times the natural log of T4 minus T over T3. Now, note that on an exam, I'll probably give you the temperatures in, oh, I forgot a term. I've got a term up here. Minus Q dot over T sub B. Minus Q dot over T sub B. Okay, so make sure we get that. I'll probably give you the temperatures in regular units, and you'd have to know that you have to put them in absolute units, so that's important here. I'm going to tell you here what S2 is. S2, I looked it up, 0.2966. S1, I looked up as 7.3594. I want you to calculate this, the remainder of here. Remember this term here. Remember what you do with Q dot. What you put in for Q dot. You don't just put in 28.76. You put in negative 28.76 as you solve this problem. Temperature boundary is going to be 275 Kelvin. Solve this problem for your lecture quiz.